In this lesson, we will discuss the general characteristics of developing flow and fully developed flow in pipes. When a flow enters a pipe system, there will be a section of pipe, called the entrance region, where the shape of the velocity profile changes in the axial direction. Here we have a circular pipe connected to a large reservoir. When the fluid first enters the pipe, the velocity profile will appear almost completely uniform and flat. However, the fluid velocity at the walls will be zero due to the no-slip boundary condition. Layers of fluid that are adjacent to the wall will experience shear stress due to velocity gradients and decelerate. As the fluid travels down the pipe, more and more layers will be impacted by this shear stress, deforming the outer layers of the velocity profile. A boundary layer forms and grows in the axial direction. Inside this boundary layer, there are significant velocity gradients and significant shear stress. But at the core of the velocity profile, the velocity gradients are still small and the velocity profile remains approximately uniform. We call the core inviscid because there is negligible shear stress in this region. As the flow continues through the entrance region, the velocity profile changes in the axial direction and the flow is said to be developing. At the end of the entrance region, the boundary layer has grown to encompass the entire flow. Shear stress exists throughout the entire velocity profile, and the flow is now said to be fully developed. In the image shown here, the profile is parabolic, which is characteristic of laminar flows. Once a flow is fully developed, the time average velocity profile does not change in the axial direction. The length of the developing region, also called the entrance length LE, is the distance required for a flow to become fully developed. The entrance length is a function of the pipe diameter d and the Reynolds number. For laminar flows, where the Reynolds number is less than 2300, one formula for calculating the entrance length in circular pipes is LE over d approximately equal to 0.06 times the Reynolds number. For turbulent flows, where the Reynolds number is greater than 4000, one formula for calculating the entrance length in circular pipes is LE over d approximately equal to 4.4 times the Reynolds number to the 1/6 power. It should be noted that other formulas exist for calculating the entrance length. We will now compare the velocity profiles for fully developed laminar flows and fully developed turbulent flows. For fully developed laminar flows, the velocity profile is constant in time. In a future video, we will prove that the laminar velocity profile is parabolic and layered, with each layer having a different velocity. The velocity only has an axial component, Vx, and the magnitude of this component is a function of radius only. For fully developed turbulent flows, the instantaneous velocity profile can change in time, and we cannot predict what the exact profile will look like from moment to moment. For example, here are 5 images of the velocity profile taken over a 10-second period. In each of these profiles, the flow is three-dimensional, with the axial velocity component being the largest. Additionally, there are swirling eddies of various sizes that cause the flow to mix rapidly. When analyzing fully developed turbulent flows in pipes, we usually do not analyze the instantaneous velocity profile because its exact shape at a specific time is unpredictable. Instead, we use a time-averaged velocity profile, shown in red, because it is constant in time. The time-averaged turbulent velocity profile only has an axial component, denoted by Vx bar, and varies radially, similar to fully developed laminar flows. However, unlike laminar flows, the time-averaged turbulent velocity profile appears flatter near the center and drops rapidly to zero near the walls. In a future video, we'll discuss how the difference in velocity profile between laminar and turbulent flows will result in differences in shear stress and viscous losses in the flow. The reason why the turbulent velocity profile is flatter than the laminar velocity profile can be understood by examining how mixing occurs in both types of flows. On the left, we have half of a laminar velocity profile, and on the right, we have half of a turbulent velocity profile. The velocity at the wall is zero in both profiles due to the no-slip boundary condition. Laminar flows are characterized by having many layers. If we zoom into the interface between two of these layers, we would see molecules undergoing random collisions. It is through these collisions that momentum and other properties are exchanged. Mixing occurs relatively slowly through these collisions, and it can take a long time before layers that are far apart to influence each other. Molecular collisions also occur in turbulent flows. However, eddies of various sizes transport fluid across the profile, greatly enhancing mixing compared to laminar flows. A consequence of this rapid mixing is that momentum and other properties become more uniform throughout the flow, resulting in a more uniform velocity profile. If a fully developed flow is disturbed, the flow will require some distance to become fully developed again. Here we have a fully developed laminar flow entering a valve. Immediately following the valve, the velocity profile is disturbed greatly. However, as the flow progresses down the pipe, it will begin to regain its characteristic parabolic shape. Notice that while the flow is developing, the velocity profile changes in the axial direction. Once the parabolic shape is restored, the flow is once again fully developed and does not vary in the axial direction.